welcome. This is Fundamentals of Micro and Nanofabrication. This lecture is on the module of additive processing, and this is the final part of the three-part series in looking at native oxides. So, specifically in this lecture, we will look at purely in silicon dioxide. Silicon dioxide interface is of remarkable high quality. I have said this multiple times in this course before. So, it is worth looking into it a little more closely and try to understand what sort of defects exist at that interface, and what sort of processing techniques we use to reduce those sort of defects. So, let us get started. So, primarily there are 4 or 5 types of defects that can exist at the silicon dioxide interface. So, supposing you have silicon and you have grown a silicon dioxide. So, first one to appreciate is that silicon is crystalline, right, and silicon dioxide is amorphous. So, there must be some transition region where the silicon dioxide is not exactly stoichiometric. So, this is what this SiOx region represents. Now, this lack of stoichiometry would mean that there are some amounts of defects because of that. So, those are typically called fixed oxide defects or QF. They tend to happen very much at the interface, at the silicon dioxide interface. At the silicon dioxide interface, but in silicon dioxide, right. The second types of defects that can occur is at the interface, but in silicon. So, these are happening because silicon is reacting with oxygen, but there is no guarantee that all silicon atoms will be bonded to an oxygen. So, if it so happens that a silicon atom is not bonded to an oxygen or to another silicon atom, then it has what we call a dangling bond. It has an unsatisfied valency. So, those unsatisfied valencies would then lead to some defects, and those defects are called interface trap defects, QIT, for the purposes of this lecture. Then as you go away from the interface, you start seeing some of the bulk defects that can exist in silicon dioxide. This is not quartz, right, this is not pure high quality silicon, crystalline silicon dioxide, this is amorphous silicon dioxide. So, you can imagine that there are some broken bonds of silicon oxygen every now and then, very few in number, but they do exist, and those sort of missing bonds or broken bonds or unsatisfied bonds would cause some amount of trapped charges. So, and those can be positive or negative and can exist in the bulk of the silicon dioxide. Another type of defect that can exist in the bulk of the silicon dioxide is mobile ions. Now, we try very hard through cleaning, use of the clean room, by using ultra pure chemicals that we never have sodium or potassium contamination. Practically, there is always a little bit of ionic contamination, no matter how much we try. And whatever that ionic contamination is would cause some amount of defects. What type of defects, I think we touched upon in the first lecture when we were looking at introduction. So, they can cause some transient effects, they can cause some hysteresis, they can cause some drift in the characteristics of the devices, etc. So, primarily these are the 4 types of defects that we have to worry about when we are looking at the silicon dioxide interface. In general, the quality of this interface is extremely good, which means that most of these defects are in the low 10 to the power 10, 10 to the power 12 range. Once again, the number of silicon atoms is around 10 power 15 per centimeter square. So, these numbers represent 1 in 1000, 1 in 10,000 or 1 in 100,000 type of defect density, which is very low. So, let us get started and look at each of these defects one by one. So, let us start with the fixed oxide charges. So, these are defects that exist in the silicon dioxide, but near the interface. So, the reason why they happen is because of diffusion of silicon. So, we have already discussed the diffusion of oxygen, right. So, you have oxygen in the gas, then you have some layer of silicon dioxide, and then you have silicon. And the way this oxide is increasing in thickness is that oxygen is diffusing through the silicon dioxide. So, there is a gradient of this oxygen and then reacting at the interface. So, at the interface there is a very low concentration, but then there is a gradient. So, while oxygen is diffusing from left to right, because the concentration of oxygen is higher on the left, lower on the right, silicon must also diffuse from right to left, because the concentration of silicon is higher on the right and lower on the left. So, this excess silicon that is diffusing from silicon into silicon dioxide causes some amount of defects in the silicon dioxide, because it makes the silicon dioxide non-stoichiometric. As these silicon are leaving the silicon substrate, they tend to leave voids. So, these are called stacking faults, and these stacking faults are also a problem on the silicon surface, but we shall talk about these a little later. So, this is the fundamental origin for QF. So, the way we reduce this fixed oxide charge density is through a post-oxidation anneal. So, if you remember in the previous lecture, I showed a generic recipe for doing oxidation on silicon, and in that recipe we had a step where we did an anneal under nitrogen for some amount of time before ramping the temperature down. And at that point I had hinted that this is to reduce defects, but did not go into the detail. This slide tells you the detail. So, this is actually a result that was published in 1967 by one of the authors, name was Deal, and that is why it is called a Deal triangle in their honor. And it is a very interesting and remarkably powerful result. So, the first thing they observed was that the amount of defect density you have at the interface, the fixed oxide defects, depends upon the ambient, which is that is it oxygen versus nitrogen, and the temperature at which the wafer is sitting. So, first thing first, as you increase the temperature while keeping the wafer under dry oxidation, the defect density falls. So, what this would tell you is that as much as possible try to grow your oxide at higher temperatures instead of at lower temperatures. So, if your thermal budget allows, go as high as possible. The second thing to notice is, irrespective of the temperature, if you anneal in an inert atmosphere, for example dry nitrogen or argon, you always maintain a very low defect density. So, this is interesting that the defect density is only high when there is oxygen in the ambient. It is does not change with temperature if the ambient is inert. Of course, inert ambient does not allow you to grow the oxide, but during annealing you do not change the interface defect density. Furthermore, this triangle is reversible, which means that you start oxidizing a wafer at around say 900 degrees C, you would get a defect density of say 5 into 10 to the power 11. If you take the same wafer and before unloading it, anneal it under nitrogen, so maintain the same temperature, but now anneal it under nitrogen for some 30 minutes or so, the defect density would actually fall. It will go from 5 into 10 to the power 11 to 2 into 10 to the power 11. So, that is why this is what this step is added to the recipe, because this is what allows you to actually grow from this point to this point, which reduces your defect density. Even more interestingly, this is a completely reversible diagram, which means that supposing you took the same wafer with the low defect density, reduce the temperature in nitrogen, the defect density would not change, but now take the same wafer and before unloading again flow oxygen, your defect density would actually increase and it will reach the number that you would expect had you done the oxidation at 700 degrees C in the first place. So, this is a state diagram. The only thing the wafer would remember is the last temperature ambient you left it. So, whatever is the last temperature and ambient that it sees, that is the defect density it shall maintain. So, as long as you add an inert anneal at the end of your oxidation recipe, you can always guarantee a low defect density irrespective of what temperature you are doing your oxidation at. Okay. So, add this anneal step and you will always have a low defect density. You would not have to worry about the temperature at which you are doing your oxidation. So, that is a very powerful result. Okay. This fixed oxide charge also has an orientation dependence. So, 100 surface and 111 surface and 110 surfaces do not all give you the same value. In general, the 100 surface tends to give you the lowest defect densities, and this is actually one of the reasons why silicon 100 wafer gained in popularity when CMOS came along. So, for BJTs it does not matter because the silicon dioxide interface is not that important, but in the CMOS technology space where field effect transistors are used, there the silicon dioxide interface is extremely critical, and it was very important for them to reduce the defect density, and the way they were able to do that is to switch from 111 orientation to the 100 orientation. So that's enough for fixed oxide charge. Let's now discuss a little bit about the interface trap density. So let me get my laser pointer. So as we discussed, these are the defects that exist in silicon but near the interface. So, and they exist because silicon has dangling bonds, unsatisfied valencies, and because of those unsatisfied valencies you have mid-cap defects. So one way to represent these defects is given on the figure on the left. So you have defect densities as a function of energy. This energy is the energy within the gap. So silicon is a semiconductor. If it's a semiconductor, it has a band gap, and band gap represents this forbidden gap where there should not be any density of states. But because this non-ideality of having these dangling bonds, at the interface you do have defects inside the band gap. And the position of these defects inside the band gap can be versus energy as well as can be plotted versus energy, and that is what this curve shows. So ideally speaking, what you should have is you should have density of states in the valence band, you should have density of states in the conduction band, and in this gap between them there should be 0. Practically that does not happen. You have a finite number of defects in the forbidden gap. So two things to notice here. Number one, there is an interface, there is an orientation dependence. So once again, just like previously, 100 is better than 111. So 100 oxidized surface tends to have lower defect densities than 111. The second thing that you notice is that you have defects in this U-shaped curve. So lower density of defects in the middle, higher density of defects at the edges, right? Let's go further. So what do we do? How do we fix this? So the easiest way we know how to fix this is to use forming gas anneal. Forming gas is just a mixture of hydrogen and nitrogen. The reason why we use forming gas and not pure hydrogen is purely for safety. 100% hydrogen is actually a very dangerous gas. It can explode if it comes in contact with oxygen. However, 10% hydrogen in nitrogen is very safe. You can safely use it in ambient atmosphere without any danger of explosions. So that's why industry likes forming gas more than pure hydrogen. So what does forming gas do? The active component here is hydrogen. So the hydrogen diffuses through the oxide, gets to the interface, reacts with these silicon dangling bonds, forms silicon hydrogen bond, and that silicon hydrogen bond is passivating and very strong, and that is what removes the unsatisfied valency and hence removes the defect. So that's the simple mechanism. On the right, the figure shows how effective this process can be. So you start with this as deposited defect density. So this is the same U-shaped curve that you saw in the previous slide. Now if you take this wafer and introduce forming gas at 500 degrees C for 10 minutes, you see that there is a more than order of magnitude change in the defect density, which is very good. However, you have to be careful, and the thing that you have to be careful about is actually what is shown in the next two slides. If you take the same curve, the same wafer, and now turn the forming gas off, introduce nitrogen, which is inert, right? Introduce nitrogen, you would actually make the situation worse. The hydrogen from the forming gas would actually come off, desorb from the interface, and as it desorbs, it would actually make the silicon dioxide interface a little worse. The defect density will actually increase. And the longer you keep the wafer in this nitrogen atmosphere, the worse it will become. So it became very good, which is curve B, and then it will become a little worse, and then it will more worse and more worse, all the way to back to where it was from where it started. Practically what this means is that the forming gas anneal step must be the last high temperature step of your system, right? Because after that, if you introduce any high temperature step, then the hydrogen that you have incorporated at the interface would just desorb, and you would actually make the interface worse, right? So it's very important to remember that for forming gas anneal, you do the anneal at low temperature, don't do the anneal at high temperature, it does not work. Do it only for 10-15 minutes, you don't need to do it for longer. But after that 10-15 minute forming gas anneal at low temperature, do not take your wafer again to high temperatures, or you will lose all the passivation effect. Let's talk a little bit about this mobile ionic charge and how to remove that. So part of the solution is to maintain cleanliness. We have already discussed surface cleaning techniques, using CMOS grade chemicals, using clean rooms, never touching the wafers with hands, etc., etc. trace amounts can be removed by the introduction of chlorine during the oxidation process. So, that is called halogenic oxidation. So, this can be achieved by using either chlorine gas or HCl. Both of them are a little dangerous. So, halogen oxidation is a little more challenging from a safety perspective, however doable. The other thing that, to care about is that both of these gases are very corrosive. So, even if you have a very high quality stainless steel tubing or stainless steel housing, etc., small amounts of leaks would cause a lot of corrosion in those steel lines. And because this is a high temperature furnace, it's not practical to have everything made of plastic. I mean, at some point you probably would need metal. So, it's a little tricky using these halogenic gases in furnaces from a corrosion perspective. But still, industry has processes to control for that, and hence it is a popular method to create very high quality gate oxides. If you do not like these two gases for safety or corrosion reasons, you can actually also use trichloroethylene, which is a liquid, or trichloroethane, which is also a liquid. So, these are liquid sources of chlorine. So, the mechanism is fairly simple. Sodium and potassium both form very stable salts with chlorine. So, they just forms the neutral salt, and that neutral salt then has a harder time moving in your silicon dioxide than sodium ion alone would. It also has an added effect that it actually captures the silicon interstitial that exists in the silicon dioxide, which actually reduces the oxide trap charges also to some effect, and that actually enhances your breakdown voltage. So, the breakdown voltage is important so that you can put, because in devices you always try to put more voltage on top of your gate, which will ultimately give you higher mobility. An added thing that we have not touched upon till now is that during the oxidation process you do tend to cause some stacking faults in silicon. So, here is an example. So, we have taken a silicon wafer in this figure, grown the oxide, and then stripped the oxide away. So, they can actually look at the interface at the silicon surface again. And if you look at the silicon surface, you will actually see these straight lines which are actually stacking faults that are forming on the surface as you are growing the oxide. So, this is especially acute when you are doing the oxidation at high temperatures. More on that in a minute. It turns out that this halogenic oxidation, because it captures the silicon interstitial, actually reduces the stacking faults. So, if stacking faults are a problem, halogenic oxidation might be your answer. However, there are some details that are interesting here. The first detail is that it really depends, the temperature at which you do the halogenic oxidation really depends on whether you want high quality silicon dioxide or whether you want high quality silicon. There is a trade off. So, in general, the higher the temperature, the defects that cause breakdown in silicon dioxide tend to increase. So, the breakdown voltage of the oxide is a little worse the higher the temperature. So, if you want higher quality silicon dioxide, you may want to do the whole process at a slightly lower temperature. However, the stacking faults are reduced in silicon only at high temperature. So, if you care about the quality of silicon slightly more, then you may want to oxidize it at higher temperature. So, there are these two regimes, and it really depends on which one you want. One thing that an industry often does is a two-step oxidation, where there is both a low temperature and a high temperature process, so that both the goals can be achieved or a better compromise can be reached. I will not actually go into very excruciating detail in this discussion, it is too advanced for this course. I will just leave this slide here for you to look at and to sort of appreciate that why, depending upon whether you want breakdown or whether you want lower interface defects, you could select one recipe over the other. So, with that, actually we come to the end of growth of native films. Finally, I just have one slide to talk a little bit about characterization. So, this is again primarily a course on fabrication, but I would still want to give you some ideas of how do you actually characterize the films that you grow. So, the easiest thing to actually do in silicon dioxide is to just measure the thickness, and the way to do that often is using ellipsometry. When you do ellipsometry, you also get some information about the refractive index, and that refractive index often correlates with density. So, the quality of the oxide, some amount of information you can glean by just looking at the refractive index and making sure it is good. and closer to the bulk value. Thickness can also be measured using simple profilometry, which is a simple stylus. So, there is a stylus that goes over a step and measures the height. For very small thicknesses, people have also used X-ray reflection, which is very accurate at giving you surface roughness type of surface roughness and density measurements. TM and SEM obviously for looking at the cross section, looking at the morphology, looking at the stacking faults, looking at dislocations, looking at the interface in great detail, and AFM for roughness and morphology. So, with that we come to an end with native oxides. In the next lecture we will start tackling the more complicated subject of chemical vapor deposition.